Okay, let's get started. Welcome. Today, we are going to be plowing forward, per usual. 5.3. 5.3 is going to introduce a new equation that we need. Daycare. Why is daycare called? Put on the speaker. Don't worry, bro. I'll be back.
So like you're a child and not doing that. Your child actually has your child
Actually happened to me.
Okay.
We're good. No. So, yeah, false alarm. No, I almost had to leave this morning. My daughter was not feeling well at daycare, whatever that means for a 4-year-old to tell her teacher. But that was just that they were just following up and saying that now she's feeling great. So it's like, okay.
Those kids, they learn dumb, like how to like get out of stuff like that. Like my brother, when he was in first grade, he woke up one morning and he's like, "Oh, I don't feel good." And I was like, "Oh, you know?" He's like, "Yeah, no, my tummy's hot." He's like, "Oh, okay, yeah, sure. But you gotta go back to bed." "Oh, no, I actually want some cereal." They're fakers. They're liars.
Oh,
You
yeah.
can't trust them.
So my son is like, he is too like sweet and honest. So like he has not figured that part out yet, and I know he hasn't figured that part out yet. He's just a sweet, honest little boy. My daughter, like she will lie straight to your face. It's like, and she has no remorse, and she'll stick to her guns. And I'm like, you are gonna just be like so much trouble. Like she's gonna be so much trouble when she's a teenager. Like literally, before she even turned 4, I had a conversation with her the one time because she had an Oreo. She snuck an Oreo, and I'm like, and then she asked for one later. And I'm like, Ava, didn't you already have one? No, I didn't have one. I'm like, Ava, I saw you. You had an Oreo. No, I didn't. I'm like, literally, I saw you. You're 3. Why are you lying to my face? She's terrifying. I love her, but she's terrifying. Yes, Dylan.
I asked my mother about Leo, and she said she's not allowed to talk about it.
All right, fair enough.
And I asked him, like, what if you send her an email saying that you can talk to her? But it's like, I still won't tell you.
She doesn't want you as the middleman, I don't think.
Apparently not.
No, you're right. All right, so let's get started. I'm sorry, that was about as clunky to a start of a class as I've ever had, which is saying something. That's not the clunkiest? All right, thanks. You're probably not wrong. All right. I mean, we're continuing it now by, okay. So we're going to go over 5.3. 5.3 is going to introduce a new equation for us today, which sounds scary because I know this unit's been kind of funky, so to speak, for a lot of you. I promise you that as we get deeper into this kinetic stuff, it will start to settle. It really, really will. I know you're probably not believing me when I say that, because I've heard quite a bit from quite a few students that they're like, I don't get this unit. It doesn't make sense. I don't like it. Just chill, okay? We'll get there. We've got plenty of time. There's still plenty of unit to go through, and it does settle. And truthfully, once we get to the test and we're kind of studying for the exam and all that good stuff, the things you need from this unit aren't that bad. The kinetic stuff on the AP chemistry test usually isn't too much of a problem. I can't speak for everyone, I guess, but generally speaking, the things that you take away from this unit that you need for the entirety of this class aren't that bad. They're really not. So hang with me. Please have a little patience and trust that we'll improve as we go. Hold on. Before I forget, I just want to find my. So we'll leave that today. All right. So let's get into this a little bit. Some review. So for any generic reaction, right, when we're talking about kinetics, again, this is just a generic placeholder of like reactant A with coefficient lowercase a. When you have a generic reaction, okay, and we're focusing in on the rate of that reaction, we're always looking at the reactant, okay? When we monitor how fast chemical reactions go, we're looking at the reactant or reactants of a chemical reaction, okay, not the products. Now, the problem with that is when we talk about rate, okay, the concentration of reactants goes down over time. So in reality, the rate would be a negative value. However, chemists don't like negative values. If you remember from 5.1, we flip the sign. Okay? If I were to find the rate of a chemical reaction by monitoring the change in concentration of the reactant over the change in time, I flip the sign just to make it positive. Okay? This is all review on the bottom now. Okay? What is K in this equation? Rate equals K times reactant raised to N. What is K? What's that called? Uh-oh. That's called the rate constant. Okay, that's a weird look. I tried to make a lowercase n, but it looked like a capital one. There we go. The rate constant. What's the label of the rate constant? What is the label or the units of a rate constant? Okay, good talk. What's the units or label of rate? Moles over liters times second. That's always going to be true, right? What's the unit or label of K, the rate constant? All right, good talk again. It depends on the other stuff. Because it matters. The order matters, right? This is the one that the label changes. It just depends upon what else is there in the expression. And we have to kind of figure it out, right? That's been part of the process that we've been going through too, is what is the label of K? And we've had to figure it out by just setting up an equation with no numbers, if that rings a bell. Did it yesterday, okay? What's N in this expression? Rate equals K times the reactant raised to the N. What's N? What's that called? All right. It is. Thanks, Maddie. I appreciate all your participation. That's the order. Now, the order is just the relationship, okay? It's the mathematical relationship between your concentration and how fast the chemical reaction is going. This is the mathematical relationship of concentration or molarity versus rate, okay? That's all old news. Now, this, I told you probably the very first day, 5.1, this probably happened, what would that have been? Last week, Tuesday, okay? How are the values of K and N determined for a reaction? Numerically, right? Like, how do I figure out what the number or the value of K is? How do I figure out what the number or value of N is? Benton? You need to have some sort of experimentation happening. You can't look these up in a textbook, okay? We need data. So, now that's kind of redundant, right? Because through experimentation we would collect data, but you know, you get my point, right? The only way I can determine K and N in my expression, in my rate law, is by, I need some numbers. I need data. So I can actually plug those things in and solve it, okay? That's all old news. Let's get to a smidge of new stuff. Graphs are gonna come back kind of in full force. That sounds scary too. I know how you feel about graphs and data tables, but again, the takeaway or like what you need to know isn't that bad. Trust me, it's not that bad. So this, we're going to start with, is called half-life. Okay, are you familiar with half-life? Not the video game. Oh, then it's no. Okay, half-life is how long it takes for the concentration to be cut in half. It's appropriately named. All right. So this is called half-life. Now, there's a symbol for this. Half-life is a length of time. Okay, do you know the symbol for time? Like the variable for time if it was used in an equation?
T.
Yeah. T, 1/2. That's half-life. Lowercase t is for time. Because what's uppercase T? What's that stand for in an expression? Temperature. Okay, so uppercase T is temp, lowercase t is time. Time, subscript 1/2, is half-life. How long does it take for something to reach half of its molarity? Yes, Ben? Good question. Depends. With what we're up to, yes. Is it always true? No. I'll talk about that as well. So here's a graph. Concentration, y-axis, time, x-axis. What's the half-life? Go ahead, stare at it, figure it out. What is the half-life of this step, of the N2O5? I think Nelson taught about it. I don't know if he had 910. Then never.
Is this possibly in biology?
I don't think so. Yeah, I think Nelson talks about it with nuclei.
Because I remember half-life a little bit, but I don't remember
I think
Where'd
in
you come from
chemistry,
You might have been talking about it somewhere.
biology though.
Maybe, I don't know.
But I don't know.
Because I know at West, the only place it shows up is in 910.
Oh.
I don't think Science 9 or Science 10 talk about it here, and I'm almost positive Bio doesn't. So somehow, some way, you know maybe a smidge.
Yeah.
What's the half-life?
100 seconds.
I agree. Now, how can we figure that out? By looking at a graph. Well, there's the original molarity. A half-life occurs when its molarity's been cut in half. Okay, well, that's nice and easy. I'm going to kind of go like this. That was ugly, but okay. This is like a half-life, right? Now, how long is that? 100 seconds. What's kind of, what often occurs is that the half-life is the same interval. So hang with me. I am now at 0.05 molarity. The next half-life would be from that amount to half of it. Okay, there it is. Now, when this occurs, okay, what's the interval? 100 seconds. If I do it again, okay, T1/2. Sorry, it's getting ugly. The interval is 100 seconds. Now, half-life, that length of time is constant if it's a first-order relationship. Meaning, this is a reactant, right? The N2O5. This is a reactant for some chemical reaction. If this is first order, its half-life will never change, regardless of what molarity it starts at, right? If it started at a molarity of 10, however long it took to get to a molarity of 5 is exactly how long it would take to go from molarity of 5 to 2.5, and so on and so forth. The length of half-life is constant if it's first order. Good news. The only half-lives we look at in this entire class are first order, which is really good. Half-life outside of first order, it's a little sketchy, requires a couple more equations and more to think about. But AP only requires us to look at first order half-lives, but it actually kind of makes sense because most things have a first order half-life. It's actually by far the most common type. First order is by far the most common order that you'll find. So that's kind of all works out. All right, let's get funky. Time for new equations. Sorry, need like a dance intro for there or something. Let's get some new equations on the board. Today, I'm going to introduce what's called the integrated rate law. Now, previously, I had shown you what I called the rate law. Okay, let me find some space here. Okay, the rate law looked like this. Rate equals K multiplied by the molarity of some reactant raised to the power or its order, right? That's the equation we've had so far. Today, I'm going to show you what's called the integrated rate law. But the integrated rate law has a different expression depending upon the order, okay? We know this can change depending upon the order too, right? If this is first order, then that's a 1. If it's second order, then that's a 2, so on and so forth. If I have more than one reactant, then I'll have more than one of these reactant boxes over there, okay? These, right there, right here, and right here, are the integrated rate laws, okay? 0 order, first order, second order. Now, these show up in your formula packet. Okay? I don't know when the last time you busted this thing out has been, but it's been a while. In your formula packet, which is looking like this, periodic table on the front, you open it up, and then there's 2 pages of formulas. At the bottom of the first page, we have the kinetic section. And in the kinetic section, you will see that equation, this equation, and this equation. They are 0 order, first order, second order. And thankfully, AP was at least nice enough to put them in order of 0, 1, 2. You never know. Okay? These are the equations we're going to have to use most often moving forward. Now, let me explain. If you're in calculus, this will make more sense. Anyone in here in calculus? I've asked that before. Excellent. These are called the integrated rate laws. The full name of this is actually the differential rate law. Okay? Derivatives and integrals, right? And if you don't understand what those words mean, good, you're not in calculus. You will in a year or 2. Okay? But we're not going to derive, we're not going to do the integrals or the derivatives between the 2 equations, but they are absolutely related to one another through calculus. Okay? Why would we need 2 different equations to analyze kinetics? It depends upon the question. Now, we have 2 equations for 2 purposes. This equation allows us to compare rate with molarity. Okay, how fast is the reaction going based off of the molarity that we have? These equations allow us to compare molarity and time. All right? More often than not, the integrated rate laws serve a better purpose from a lab perspective. Here's why. It's easier to monitor time in a lab than it is to monitor rate of reaction in a lab. You know what I'm saying? How do you monitor time in a lab? Yeah, a stopwatch, a clock, a phone, whatever, right? It's pretty easy to monitor time throughout the lab. And there are ways, pretty easy ways, to monitor molarity during a lab. So oftentimes, the integrated rate law, one of these 3, again, it depends upon the order, but oftentimes these are actually more useful than the differential rate law, or what I previously had just called the rate law. Okay? Now, these look a little funky. Okay? We have concentration with a subscript T, concentration with a subscript 0. When you see a subscript of 0, does anyone know what that means? Initial. Okay? It means initial. Now, oh, I say that over here, don't I? Hey, look. All right. So all 3 of these equations have 2 molarities for the same reactant show up. Okay? One of the reactants, or sorry, one of the places is going to be the molarity when we started, the initial molarity. That's the subscript 0. It actually means naught, okay? And it's where's the molarity when we first started our experiment. The other molarity is at some specific time. And it depends upon what the question's asking and what we want to know. Here's the thing though. The little subscript T and the t that we use in the mathematical equation are the same time, okay? So if I say I want to know the molarity at 100 seconds, I will plug in 100 seconds over here, and then I'm solving for that molarity at 100 seconds. That makes sense? Okay. So let me go through a couple other things as well with these new equations. All right. We can graph these things. We can graph concentration versus time. Looks like this. Concentration versus time. Okay. When you graph concentration versus time, if you get a linear plot, meaning a line, right, it actually tells you the order of the reaction. And you just hold a minute. Okay. If the plot of concentration versus time is a linear graph, okay, it's a zero order reaction. Here's first order. This is natural log of concentration. If you graph the natural log of concentration versus time, and you get a line, it's first order. And last but not least, this is 1 over the concentration. If you graph 1 over the concentration versus time and get a line, it's second order. We can use graphing relationships to figure out the order as well. The previous way we figured out order was by looking at data, right? That was called the method of initial rates. And it's like, okay, from trial 1 to trial 2, this doubled. And the rate doubled, so therefore it's first order, right? This, we're going to be looking at graphs. We'll have 3 graphs: concentration versus time, natural log of concentration versus time, 1 over concentration versus time. One of them is going to be a line, the other 2 aren't. Whichever one is the linear one will tell us what order we have. If concentration versus time is linear, it's zero order. If natural log of concentration versus time is linear, it's first order. And if 1 over concentration versus time is linear, it's second. Okay, we'll practice that in a little bit. The other thing that really matters is if you have a linear plot, the slope is the rate constant. Okay? Sorry, that was a bad transition. Okay. The K value in this reaction, or sorry, in this equation, is the same K in the other equation. It's the exact same thing. It's still the rate constant. It shows up in both of our expressions. To solve for it here, we usually plug some numbers in to solve for K. To solve for the rate constant with the integrated rate law, oftentimes we just use the linear graph. If I know that natural log of concentration versus time is the linear graph, the slope of that is K. Now, it actually ends up being negative K. But here's a good thing. K is never negative. So spoiler alert, if you think you got a negative value of K, just flip the sign and you're good to go. We'll practice that too, okay? The last thing I have on here is this. This is the last equation you have in your formula packet in that section. This is for half-life. Sometimes you're not given a graph and you're asked to solve for half-life. It's really, really easy. 1, if you're asked about half-life, it's first order. It has to be. AP does not ask any half-life question unless it's a first order reaction. And if it is, if you know what K is, the rate constant, this is the math. You take 0.693 divided by K. That is the half-life for a first order reaction. It's super, super, super simple. If people screw up half-life problems on the AP test, it's because you don't use your packet and you don't realize how easy it is. Like, there is zero reason why any of you, anyone, anywhere in the entire country that takes the AP Chem test should get a half-life problem wrong. Because they are about as easy as anything on that entire test. Because the equation is this, and it's even in here. All right, enough yapping, okay? Well, actually, sorry, a little more yapping. These are in your packet. Okay, you don't need to memorize them. Please don't memorize them. Use your packet. Okay, this is in your packet. Please don't memorize it. Use your packet. That's what you're allowed to use that on the APA test. Okay. Let's use this stuff now. Okay, here's a graph. Okay, here's a graph. Is this 0, first, second, or third order? Use the little previous note chunk. Figure it out. Is this 0, first, second, or third order just looking at this graph? Show me with fingers. And if it's first order, please use the appropriate finger. Nope. Probably not a good choice. What is the order? Nope. We don't. Yeah, we don't. No math involved. All we need is observational skills. Is this graph linear?
Yeah.
Yes, it is. What are we graphing? What versus what? Natural log of concentration versus time. If we have a natural log of concentration versus time graph and it's linear, what's the order? It is. It is. Now, eventually we'll do enough of this stuff where you'll just kind of memorize where it's like, oh yeah, if concentration versus time is linear, that's 0. If natural log of concentration versus time is linear, that's first. If 1 over concentration versus time is linear, that's second. You will just know that offhand because we'll do enough of this kind of graph recognition stuff. All right? But for now, please look it up, right? Go to that little chart on the bottom of 5.3 and look it up. What are we graphing? Okay, natural log. Hey, it's a line. Sweet, it's first order. There's nothing else to even think about. Okay? We look at the labels and we find the linear graph. So this is first order because, well, the natural log of concentration versus time graph is linear. That's all we need. That's the only explanation we need at all. If you get a linear graph of natural log of concentration versus time, it's first order. Calculate the value of the rate constant with the help of the data up above. And by up above, I mean not up above on my slide, but on your sheet, I think it's up above. Is it? Excellent. Okay. From that graph, what did we learn? What did we just learn? It's first order. So which equation should we use? The first order one. Now, again, no need to memorize it. Don't waste your time. If it happens by accident, that's fine, right? That just means you're using it enough to remember it. But don't bother. I'm just going to look it up. I need the equation of the natural log of the concentration at time t minus the natural log of the concentration at time 0 equals negative kT. Now, what's a little tricky is the data I've provided already has done the natural log mathematical process, right? These are not molarities. These are the natural logs of molarities. So here's what the question asks us to do. Find the value of the rate constant. We want to solve for K. What's the initial, or sorry, let me say that again. What's the natural log of the initial molarity?
-2.3026.
This one. Times 0 is initial. 0, 0. That's the one we want right there, right? So I'll leave some space here, but I know I'm going to subtract negative 2.3026. I don't know what K is. Okay. Now I have the other two chunks. And I have the natural log of concentration at time t, and I have time t. Does it matter which one I pick? No, it really shouldn't. This is a linear graph, by the way, right? These data points were the ones that were graphed on the previous graph. So it shouldn't matter, but when you're dealing with a line, assuming we have perfect data, who cares? But let's just, for the sake of argument, assume we don't have perfect data, and I'm going to pick the furthest point away. Okay, I think I made this where it is perfect data, so it doesn't matter which data point you pick. But I'm going to use the bottom. So I'm going to say my natural log of concentration at time t is negative 5.052. Sorry, negative 5.0752. And my time is 400. We'll put a decimal there just to give us 3 sig figs. Go ahead, solve for K. Watch your negative signs. That gets a little annoying. What'd you get? Sounds good to me. I'm going to write it in scientific notation. You don't have to. Perfectly fine if you didn't. Now, this is the rate constant. What's the label? Oh, gosh. Now, here's the deal. This is the integrated rate law. This is the first order integrated rate law. The first order differential rate law also exists. We didn't need it to do the math here because we were asked about time, or we were given time and concentration instead. But this equation also exists. It is way the heck easier to determine the label of K from the differential rate law than it is to determine the value of K, or the label of K, from the integrated rate law. Okay? So, again, there's two ways you can get the label of K. The first way is, and the way that I've kind of taught you, is to use this rate law and plug in no numbers, just labels. I have rate. I have K, which I don't know. I have molarity. What am I missing? What does the label of K need to be in order for this left-hand side and the right-hand side of the equation to be equivalent? Correct. 1/2 seconds, or s to the -1 power. Okay? Now, by doing the integrated rate law up here and getting this value of K, it's harder to mess with labels and units to understand that this is a label of 1/seconds. Okay? You need the label. It must be there. Again, you can do all this nonsense, or you can just start memorizing that structure of the label of K. The label of K is liters over moles times seconds. The power of the liters and the power of the moles is the order minus 1. Again, if I have an overall order of 5, the label of K is liters to the 4th over moles to the 4th times seconds. If I have an order of 8, the label of K is liters to the 7th over moles to the 7th times seconds. The hard part is with first order, then I have liters to the order of 1 minus 1, which means 0. Liters to the 0 power equals 1, goes away. Moles to the 0 power in the denominator goes away. What am I left with? 1/seconds. Okay? If you're struggling with that, I can help you. It just takes a little bit of time to break through that nonsense to figure it out. All right. Use the answer from the previous question to calculate the molarity of N2O5 at 150 seconds after the start of the reaction. This takes some brain power. What I want is molarity at 150 seconds. Okay? Which equation should I use? We have a couple options. Which equation should I use to solve this? These are the questions you're going to have to ask yourself in this unit, is what equation do I need? If you can answer that question confidently, I'm not saying you can right now, but eventually, if you can answer that question confidently of, I need this equation, then you're in good shape, because then it's just plugging and chugging. Dylan. Say that again? Yes. As a matter of fact, we have to. Okay? We have to. This is still first order stuff, right? I can't switch. I can't switch to the 0 order one. It's not 0 order. I can't switch to the 2nd order one. It's not 2nd order. I must use the first order reaction for the equation. That's what it is. So here's what I have. I have the natural log of my concentration. I'm just going to use A again, even though it is the N2O5, at time t minus the natural log of my concentration at time 0 equals negative K T. Okay, what do I all know? What can I plug in? The initial, this whole thing, right? I know that. It's from my data table. Let's plug that in. So I have the natural log of my concentration at time t minus a negative, what was it, 2 point something? 26? Okay. What else do I know on this side? I do. What was K? 6.93. And what was T? Yeah, okay. I need to use the time that it's requesting. I have everything I need, but here's the deal, right? When I'm all done, do I want the natural log of concentration or do I just want the concentration? I just want the concentration, which means somehow, some way, I need to get rid of that natural log. Do you remember how to get rid of logs? Yeah? Okay, go ahead, get started. If you don't, we'll go over that one more time here, help you out. I'm just going to organize, I think, and isolate my natural log of nonsense and all the number stuff on there. So. Okay, I'm just at an intermediate step. That's all I'm doing right now. Okay, I've got all my numbers, numerical stuff organized on the right. I've got my unknown on the left. What do I do to get rid of that natural log? What do I do?
Use a normal one.
Can I use a normal log? Well, what is natural log? Let's start there, I guess. What is natural log? Correct. Log base E, right? When we normally do logs, we're talking about log base 10. Okay. And how do you get rid of it? Correct. Yeah, logs and exponentials, fun stuff, right? So we're going to get rid of the natural log. The way we do that is we take the base of that log and we raise everything, the base raised to the power of everything on each side. So I'm going to take the mathematical constant e raised to this power. Now what does that do? The e and the natural log cancel each other out. And what am I left with? Just molarity at time t, which is what I wanted to know in the first place. On the other side, I have to punch this into my calculator. Mathematical constant e. It's a lowercase e. It depends upon your calculator, but it's in there somewhere. Okay, you might have to go searching for it, but there's mine. When I take e to the power of negative 3.3421, I get a molarity of 0.0354. Okay. What's the label? What did we just solve for? Molarity. So it's, you know, molarity. Or you can do mole over liter. Okay. Now I should probably get rid of the A and say what this actually is because I'm at the end. Okay, that's an ugly 5. And in reality, if you wanted to write 150 in for T, you can, because that's exactly what it is. Yes?
On the like AP test, you just go into your like TI inspired.
Yep.
You solve.
Yep. Yes, solver is allowed on the AP test. Huge advantage. But you don't need it. People that don't have solver and don't have a TI, whatever the heck, you're fine. I promise. Like you can do this without a solver because you're smart. All right, let's double check one thing. Okay, let's double check one thing. I wanted to know what the molarity was at 150 seconds, and we said it should be 0.0354. Let's go back to the graph. Not this one.
No.
This one. 150 seconds. What did we say it should be? 0.0354? Does that look about right? Yeah, and it should, right? That's why I'm doing that. Like, does my answer fit in with the rest of my data? And if it doesn't, you've done something wrong. You know what I'm saying? So you can kind of double check your work sometimes if they've given you some nice graphs and data tables. Did what you just solved for fit in where everything else should? Yes, okay, that's good. That means we've done the math appropriately, we've done everything else appropriately, and we've arrived where we need to arrive. A first order reaction has a half-life of 20 minutes. Calculate the rate constant for this reaction. How do I do this? I was given one single number, 20 minutes. That's it. And they want me to solve for K. It sounds so confusing until you realize it's really, really easy. How are we doing back there? Good? Good.
I mean, I'm doing good.
Good. Making sure. Are you mimicking my hand motion? Anyway, what equation do we need?
E sub 1/2 equals 0.693.
That's it. It's super easy. That's it. So what's T1/2?
Half-life.
Yep. And what is it? 20 minutes. So 20 minutes equals 0.693 over K. Solve for K. Careful, you gotta label that thing. But, you know, the math is easy. Sorry, this is a lowercase k. It doesn't look like one because I can't. Whatever. With 3 sig figs, I guess I'll go there, right? What's the label of that K? Correct. Not seconds, because why? Well, they gave us minutes. That's why. And in this one with half-life, right, it's always first order. So it's always 1 over time. 1 over seconds, 1 over minutes, just depends upon what they gave you the time. And even if you didn't know that, this is a label-less value. And if I solve for K, I have a label-less value divided by 20 minutes, 1 over minutes. Make sense? Cool. One more thing, then we'll call it a day. Use this formula to find how much time is required for this reaction to be 75% complete. Here's the formula. Okay. No numbers, no molarities whatsoever, just a percentage. How long does it take for the reaction to be 75% done? Okay. Yes. Yep. Thank you. Good. Yeah, so let's think about it, right? What does 75% complete mean? What does that mean? 75% complete. What does that tell us about the molarity? Okay.
Or, I mean, I'm sitting at the bottom.
Does that mean it's 75% of the way to being like half the molarity of the originally was?
Yeah, okay. So we're not doing half-life.
Okay.
So just a chemical reaction is happening, right? Now, remember, maybe this will help, okay? In this equation, A is a reactant, right? It's always a reactant. Always. So if I have some reactant at the start, how much reactant do I have when it's 75% done?
75 times.
I have 25% of it left. Right? If I have 100 at the start, which, again, that molarity doesn't make any sense, but that's fine. If I have 100 at the start, how much do I have when it's 75% done? I have 25, because 75% of it's gone. Because 75% of it's been used. Make sense? So I didn't give you molarities at all, but we don't need them. All we need is that ratio. I could pick this starting molarity to be 1, it could be 100, it could be 523. Doesn't matter. As long as I plug in something here for its starting molarity, and I plug in 25% of what I originally had here, it's going to work out. It just matters that the ratio is correct. So no molarity is needed. How much is left, or sorry, how long does it take for 75% of this reaction to be all done? Let's plug in some values, okay? All right, so I have natural log of 25. I'm using 125 just to make life easier. Okay, minus natural log of 100 equals negative k. What did we just solve for k in the previous chunk? What was the rate constant? This is, I'm sorry, this is a continuation of the previous problem. I don't know if it explicitly says that. Yes, it does. Otherwise, we don't have k, right? And it can't work. Sorry, this is a continuation of the previous half-life one. So what was our value of k from the last problem? This one. Sorry. 0.0347. Short-term memory. And what don't we know? T. Go for it. With sig figs, I'm getting 40 minutes. Because this is in minutes, right? This was 1 over minutes. So when we solve for time, it has to be in the same unit of time that our k value is in. Now, here's the deal. If I have 1 half-life occur, how much percentage of my reactant is gone? 50%. If I have a second half-life occur, how much of the original is now gone? 75. So if 2 half-lives occurred, I have 75% of my reaction complete, or 75% of my reactant gone. We said the half-life in the previous problem was 20 minutes. Does it make sense that at 40 minutes, 75% is gone? Makes absolute perfect sense. We did it correctly. Okay. I hope again, it's more mathematical today. It's more mathematical once we start using the integrated rate law. But for some of you, that's nice and easy. You can plug and chug all day long and you're good to go. All right, I'm all done. Have a lovely day, people at home. If you're joining in, I appreciate it. People in front of my face, grab a wipe and share a wipe and sanitize your area, and we're good. We'll catch you guys tomorrow.